Okay. My exam is in 2 hours. I kind of overslept, so it's 6:55 a.m. I woke up at 5:30, but fasting started at 5:16. So I woke up at 5:30 and was not able to eat. Whatever. So I'm gonna have to thug it out for my exam. No food, no water. But hopefully we'll live. Just gonna go quickly here before my exam. I'm just gonna do some review and then that'll be it. Easy peasy. Just make sure I'm really prepared for the exam. Let's set up my thing. So I got my equation sheet made. It's 8 by 11, double-sided. Not a single handwritten piece of text on either of them. The one side where I did all the textbook problems, it's really difficult to read because it's really small. So, we'll get through it. I'm thinking I might just speed run the homeworks. Imagine that's the best thing to do. The problem with doing the practice problems is that they're impossible, and each one of them takes like an hour by itself. So I think I'll go through the homeworks but in reverse order. I typically do this anyways for exams, is the homework in reverse order. Okay. Here we go. Alright, let's just get started. No wasting time. No wasting time this morning. Okay, so we're on homework 3. Question 1. Odd functions. Okay, so this is a finite square well. The problem is, I kind of remember these questions by heart. It's like f e to the something. We'll just use my equation sheet, actually, because if this information is not on my equation sheet, then we'll have a problem. And we want odd functions, so we need sine. Okay. And this doesn't have a time dependence. So now what does it want me to do? I'll use the continuity of the wave function. Okay, so by continuity, we know that well, actually, wait, okay, hold on. What do we know by continuity? We know that the wave function is continuous. So c sine ax will equal no, not ax, la. Okay, but maybe more importantly, wait, let me try to recall. Something's supposed to equal like 0 or something. Oh, you know what? No. Okay, no, I see. So the continuity says that psi is continuous over, well, it's free particle, so there's no bounds, but we also have d psi dx is continuous. So now we have c cosine LA equals minus k f e minus ak. Yeah. And so now we have to divide both equations. We'll divide the derivative by the normal function. So we'll just get cosine L by LA sine LA equals minus k. And then we have this, we have z equals LA, and this needs to be on my equation sheet. Actually, it's not on here. K is supposed to equal something. But regardless, wait, hold on. Z equals LA. Yeah, that's fine. It's like Z by Z naught. No, Z naught by Z. Z naught by Z squared minus 1. I don't know. I think I gotta just do that somehow. I mean, regardless, the solution is cotan of Z equals root Z naught by Z squared minus 1. That's the solution. So I actually I need that thing from the book. What problem is this? 229. Yeah, I need this on my equation sheet. It's not on my equation sheet. It's this here. Hold on. K equals L tan. Yeah. Okay, so he says KA equals root Z naught K squared plus L squared. Wait, hold on. Let me follow what he's doing. Tan Z K by L. Oh, I'm forgetting a thing here. This should be CL cosine theta. Oh, I see what's going on. Wait, Z equals LA. Oh, I already have that. But then K, yeah, I don't have this K here. K equals, oh, I guess I do have it on my equation sheet. Okay. So I'll leave this on my equation sheet the way that it is, and I can derive it from that. So I have Z equals LA, and then I have Z squared plus KA squared equals Z naught squared. So this gives us KA equals root Z naught squared minus Z squared. Right? Dividing both sides of the equation, we get CL, no, we just get L cosine LA by sine LA equals minus K. Okay, and so we have to plug in Z and the L. That's what my problem was. So L is Z by A. So we have Z by A cotan Z equals minus K. L. Wait, hold on. Divided by Z. Yeah, that's fine. Yeah, that makes sense. Okay. So we have minus Ka divided by Z equals cotan of Z, right? And so we'll bring the Z inside of the square root, and we'll get Z naught squared, Z naught by Z squared minus 1 equals minus cotan Z. There we go. And that's our solution. Okay, next part. Solve it graphically. The graph is just going to look something like this. So we'll have Z naught whatever squared, and then actually it's going to be more like this. It's going to be more like that. And I also have this graph on my equation sheet, so yeah, it's going to be like this, and then like this. Like that. Okay, next, B, consider limiting cases. Okay, the limiting cases are just when you have a wide, deep well and a really shallow well. And it's not on my equation sheet either. Oh, but yes it is. Yes it is. On this side here. So when you have a wide, deep well, if you have a wide, deep well, the intersections are at pi, 2 pi, 3 pi. When n is even. And then you have a shallow, narrow well. You have no odd bound states. Okay, next question. Evaluate the following intervals. I'm actually not doing this one because it's just too easy. Oh. This question is also pretty easy, but it's just really annoying. Okay, let's find the position wave function psi of x comma 0. This is a free particle, so we have well, it actually doesn't matter if t is 0. Doesn't matter if t is 0. Increase music sound a little bit. Okay, increased it a little bit. Okay, I kind of feel like I'm missing the equation here. The thing about this is t equals 0, so I'll just do ikx. I think I can do that, so we'll say x of 0. So this is going to be 1 over root 2 pi. This has no time dependence. So we're going to have just times e to the ikx. 2b squared divided because t equals 0. Okay. So we need to convert this into, so we're going to use a u substitution. We're going to say u equals k minus k naught, du equals dk. We're saying minus u squared b squared what is k equal? K equals u plus k naught. So we're going to pull one part of this out. So ik naught x comes out of the equation. And then we're just left with u squared b squared plus iu x, which will do complete the squares. So minus a, which is b squared, u squared, and then ix u. So this equals minus a, so minus b squared outside of u minus ix over 2b squared plus minus x squared over 4b squared. Okay. And so all that stuff comes out of the integral x comma 0 equals 1 over ik naught x e to the minus x squared over 4b squared. And then we get the integral of e to minus b squared u minus which equals, just copy all this nonsense, root pi over b squared. Right? It's just pi over a. Yeah. And so you can probably simplify that. I'm not going to. Tells us that each plane wave of psi k has frequency omega k. Okay. Hold on, let me think here. Bro, the writing on this equation sheet really is quite small. Like, actually, I can't really read this. No, it's fine. like I'll need to read like this stuff exactly. I just need to make sure I know the concepts and stuff. Like this one, kind of forgot what I did last time. Each psi k has a frequency. Okay. Yeah, the problem is I don't see how this time dependence comes in. It's omega k. I remember okay, so the time-dependent Schrödinger equation. Okay, if I remember this correctly, so we take the time-independent Schrödinger equation. Well, first of all, we have to find the derivative. With respect to t. No, that's not right. Okay, I don't really remember how I did this now. Oh. Yeah, I did a Taylor expansion. What a drag. Wait, Taylor expand omega. Taylor expand omega. What did I do? Dude, that is so stupid. I did k naught plus k minus. I said k equals k naught plus k minus k naught. Dude, that is the stupidest thing I've ever seen. What a joke. Wait, where? Why do I not have Taylor's Taylor expansions on my equation sheet? Let me write it out. Need a pencil. Where's my most goated pencil of all time? Here it is. So this is the only free particle question I'm gonna write, so I can write whatever I want. This is the right equation sheet? Yeah, it should be. Okay. So I didn't even Taylor expand it, actually. There's no Taylor expansion here. I literally just squared it. Yeah, right? That's all I need to write on my equation sheet is this equation. K equals k naught plus k minus k naught. And then we just take this squared. It's going to equal k naught squared plus k naught outside of k minus k naught. Plus k minus k naught squared. You have both terms in their cross term. Okay. And so okay, what does the question ask? It says omega naught plus VG k minus k naught. So omega naught equals h bar k naught squared by 2m. VG equals h k naught over m. Oh, wait, where'd the 2 go? Two. This is a 2 here. That's why. There's a 2 here. For the cross term has a 2. Okay. And the last one it wants from me is beta. And beta just equals h bar over 2m. Okay, can I check my... Let me check my answer. Oh, well, let me do C first, and then I'll check my answer. Oh, nah, bro. This is actually the most annoying thing of all time. Oh, no, you're actually tweaking. Wait, okay, I actually did have a question for this part, though. I just write e to the minus, yeah. Why did I even solve this integral again? So stupid. You literally just add this factor of yeah, it's the same exact thing. Yeah, because the integral's with respect to k, so like there's literally no point to redo the integral. What you end up getting is just this. e to the minus I omega t. Oh, omega is a function of k. Oh, crap. You can't be dead serious, bro. Oh, no, yeah, I don't have time for all that. You do have to redo the integral. You do have to redo the integral. Yeah, ain't nobody got time for that, bro. Let me just make sure my variables are right. Oh, they kept the z actually on theirs, but I divided by z. It's the same thing though. Whatever. Problem 3. Yeah, beta equals h bar over 2m. That's the only one I had concerns about, but easy peasy. I mean, the main point of going through all these again is to ensure that I have all the equations on my equation sheet. I obviously can solve all these questions, and given enough time, I can solve them pretty easily. But I just need to make sure my equation sheet actually has all the information that I need. Oh, infinite square well, so easy. All right, I'll be right back. Okay. So, homework 2, question 1. Yeah, infinite square well is pretty easy. So infinite square well, v equals 0 in the well, and v equals infinity else. Okay. Let's get to the wave function. So a wave function itself will be positive. X will actually also be positive because it's an infinite square well. So we come from 0, and then we're going to have some function after that. Oh no, we're sketching the wave function, not the potential. Oh no, that's what I said was actually right. So let's think about this. Let's take a u substitution just to make this easier to see. So our dominant term is going to be u cubed minus u squared plus u. Essentially, I mean, we can throw on these constants, but they won't really make any difference. The dominating term is u. So let me factor out a u, or u squared, which equals like u, probably u minus 1/3. U plus 1. No. U plus 1/3, u minus 1. U minus 1/3, u minus 1. Right, you get u squared, u by 3, u plus 1/3. Yeah, okay. So this is our function. So, how do you graph things? So at u equals 1/3, it's going to be 0. At u equals 1, it'll be 0. U equals 0, it'll be 0. But I'm like 90% sure the wave function can't be below 0. The wave function. Maybe the wave function can go below 0. But then it's just going to be like a squiggly line. It's going to be... Okay, so... I guess they felt like skipping the graph in the solutions. Yeah, I guess... Why did I think the wave function couldn't go below 0? I thought it was a probability distribution, though. I guess psi squared is the one that's a probability. Yeah. Okay, it's easy enough. Okay, now let's do an actual question. The purpose of normalizing it, let me just normalize it. I bet that's what it means, what it wants me to do. Wait, I actually don't want to normalize this. Yeah, it's just too much algebra. Okay. So my strategy for obtaining the wave function as a function of, with time, the time-dependent wave function, I would say I would do this. Psi x comma 0 dx, which would give me some function, and psi of n, of course, is root 2 over a sine n pi x by a. And so I'd do a u sub x by a, solve that integral, and then plug it into this equation here. Psi xt equals cun psi n e to the minus. That's what I would do. So you'd probably get like some sine squared, some other stuff. For using your result from B to find the probability for an energy measurement to yield one of the allowed energies of the infinite square. Well, so the allowed energies are these ones. I would need the expected value of H let me think about this. The probability no, I wouldn't want to do that. What did I do? Are we dead serious? Well, first of all, this isn't on my equation sheet. First of all, this isn't on my equation sheet. Oh, bro. Okay, it doesn't need to be on my equation sheet, actually. Yeah, it's just me deriving these formulas for some reason. I already have those. C of n. Yeah, I already did. Oh, this is the part that I said. I'm on C. That's why. Yes, there's only E of n. The probability of an energy measurement is, is 1 equals a summation of C of n squared. Yeah. What was our C of n? Yeah, it would have been something stupid like that. Yeah, it was. Yeah, so you need your C of n, and then you can take the opposite value squared. Wait. Oh, I see. I see. Yeah, I see. Let me just make sure. n is odd, then that will be negative 10. Wait. Absolute value. Oh, squared, sorry. $420, yeah. And then for even, it's gonna be 8, it's just gonna be the same thing, but 8 plus 10. You get 34,020. Yeah, exactly. Okay. Alright, next part. Using the result from the previous part to calculate the energy E. Yeah, okay, wait, actually. Okay. Yeah, this 100% has to be on my paper. So, the expected value of energy equals and V is 0 for infinite square well. Okay. The music is the Ghibli. I don't know what it's called in the description, but it's a Studio Ghibli playlist. E does not depend on time. believe 2.45 is on my equation sheet. Oh no. Yo, 2.44 is on here twice. Oops. 2.44 is on here twice. Should I improve my equation sheet? I don't think it'll help at all because I have nowhere to print. Pretty sure the printer is closed. And it just seems like too much work. If I wanted to make it better, this is what I would do. Put this like this. I'd move this whole column down here. But I'd split it into two columns. I guess I'd just split it into three columns. Something like this. Yeah, it wouldn't work. Just leave it. It shows that the number of nodes of stationary state always increases with energy. Oh, okay, I remember this. You're basically saying that like this is side 1. Side 2. And this is side 3. A node is just every time it crosses the x-axis. Okay. So we have to do product rule on each one. You'll end up getting some long thing like some long thing like this, and then you have one more factor. Okay, and so these are just the same thing. So these get deleted. And so you're left with this. Minus this. But of course we know that d squared psi m dx squared equals something. This is in the infinite square well, but one-dimensional potential. Okay. independent Schrödinger equation. Okay, I see what we do. So this equals E of m psi m minus V psi m 2m over h bar squared. And this will be a negative sign. Okay. The problem is that I'm not getting these potentials to cancel out. Oh, yes, I am. Okay, yes, I am. So you're going to be left with em psi m psi n. This is a negative. This is a negative. We have 2m by h bar squared. This one is going to be a positive v psi m psi n 2m over h bar squared. And then this is going to be, the minus sign will cancel out, so we'll have plus en psi m psi n 2m over h bar squared minus v psi m psi n 2m over h bar squared. Of course, these are just the same thing, so we're left with psi m psi n en minus em 2m. And that's what it wanted us to prove, right? Nice. Easy money. Let them be two adjacent nodes, show that this equals that. I remember this solution. I was like, what is he talking about? Oh, you just integrate both sides of the solution from part A. Yeah, just integrate both sides of the solution. This is trivial. And you're left with psi m prime psi n minus psi m psi n prime equals, this is all constants, and you get the integral of this. Literally, all you have to do is integrate this. We already proved that this is true, so you just integrate both sides with respect to x. And that's it. Oh, I guess you need to use your bounds. So this is the integral, but it goes from x1 to x2. And this will go x1 to x2. Okay, and then we have to prove, and then we have to show that the stationary states are orthogonal. Right, so we have xm prime x2. Wait, aren't we supposed to have cross terms though? Oh, I guess no. No, we're not. We don't use orthogonality here, actually. Wait, actually, how are we not using orthogonality? What does orthogonality say? Maybe we can't just do that. Wait, do I really have to integrate that thing? Wait a minute. Yeah, wait, this is exactly what I have. Wait, so how did he get rid of those two? Wait, okay, so they're right next to each other. So one is going to be even, one's going to be odd. If we choose n to be even, n to be odd. No, it still doesn't give you 0. Wait, how do those cancel? How do these terms cancel? Okay, it doesn't even know what it's saying. Only 2 of the terms vanish. What? This whole bracket does not become 0. This thing is useless, bro. doesn't know nothing about anything. Yes. See, this is what I wanted. What? Oh. Yes, that's correct. Yeah. So it's a node of 1. Oh wait, what did the question said specifically psi m? Where's the question at? Oh, they're nodes. I didn't read that. Yeah, see, that's what happens when you try to speed run. I didn't read that they're nodes. So any term with just psi m, the derivative is non-zero, obviously, but the function evaluated at those points will be 0. It's a definition of a node. This question is so easy. For a particle in the nth stationary state in the infinite square well. What wave function do we use? Alright, bro. Bro, how do I see that? Yeah, just use this one. Wait, how did x equal a over 2? You get what? 2 by a. Right? From 0 to a. Yeah, you get a cosine. Yeah, because they're both odd. Wait, are they odd? Wait, is sine squared odd or even? Sine squared is even. Wait, why didn't I show my work for this question? U equals n pi a. This equals a by 2. No one wants to prove it. Yeah, I don't have any of these. Is that a Rotring? Yeah, it is. It's a Rotring 800. I should write the integral for sine squared. Because this might be on the exam somewhere. Integral of sine squared. What's the integral of x sine squared? This one's way easier. Okay. Oh, linearly independent. Yeah, just change the sign of one of them. Has the same energy and just change the sign. Yeah. You have all this is so stupid. But yeah, this is the principle of orthogonality. If you have the integral of two different states, it evaluates at 0, so you only have the pure terms, no cross terms. And then this also all has to equal 1, which we checked. And then have the same energy probabilities. Okay, yeah. You just flip one to be a minus. Okay, and then the second part B yields the same expected value of h. So the expected value of h is the sum of the coefficients times their energies. So E1, you have a factor of E1 on all of them. So it's going to be E1 root 1/2 E1. And then, oh, it's squared. It's going to be 1/2 E1 plus 4/6 E1 plus E3, or E3, no, E1 plus E1, 3/2 root 4/6, 2/3. Oh, that's annoying. But you're going to end up with some fraction. Yeah, summation. Yeah, 25/6. Oh, it's 9/3, so it's 1/3, or it's 3. Yeah. Then your two conditions are that the sum of the probabilities equals 1, or the probabilities are equal to the coefficient squared, and that we get the same exact expectation value for h. Yeah, easy peasy. These are both on my equation. You just do the two cases. And then, bro, homework one was so trivial. Like, I actually probably don't even need to study homework 1. I don't even need to pull it up. Oh yeah, don't even look at that question. Yeah, standard deviation, normalized wave function. Pretty straightforward stuff. Let's see. Once. Yeah, I mean, they wouldn't ask us something like that on the exam, so. I mean, you need your textbook to solve that question. Like, you need all the equations in the textbook. Okay, I think I'm done. That's it. I'm packing it up. My exam is in an hour and 15 minutes, so probably gonna play some chess. Just chill. I'm gonna get to the lecture hall at 9. The exam starts at 9:30, but I like to get there early. So I'll probably leave my apartment here in like 30 minutes. So goodbye. My exam is an hour and 18 minutes. And I literally have nothing to study. Like, I've studied it all. There can't be. I don't see any reason for me to continue. So good luck, bro. Thank you. Goodbye.